So we start with a controversial question. Is the multicore dead? And I would like to get your feedback and a lot of interaction from you. Also, it's the last session, so just to keep up. So first, I would like to invite the panel members. Per Stenström from Chalmers University, expert in computer architecture, runtime management of cache memories, and hierarchies. Per, could you please take the microphone as well? Yes. Followed by Davide Rossi. Davide Rossi comes from University of Bologna. He's an expert in ultra-low power platforms, so energy efficiency. We have also Johan Gronqvist from ARM, Lund. He's expert in hardware software co-design and GPUs. And Stefanos Kaxiras, Uppsala University, computer architecture, cache coherence, energy efficiency. Thank you. So while we are getting ready, I would like to start from the beginning of the multicore. Once upon a time, we had many years ago, chip designers realized that single core processors were not scaling anymore. So they reached their limits in performance, and overheating became a critical issue. Now, just to warm up, many years ago, how many that means? Your turn. 13? Yeah, around there. Around there. About 10, 11, so it was a good guess. 2007, more or less, was when single thread performance could no longer scale. So we have, if we're looking at number of transistors, they could double their number almost every 2 years, then they reach every 18 months. We have also frequency that is increasing and increasing until in 2007 it would no longer scale. We also had power issues, right? So it was around here. We have it in blue, where we could see that there was no longer a solution to have single-threaded cores. So the solution was multicore, but multicore was not only the answer to performance demands, but also introduced a breakthrough in computing. So multicore architectures required multicore programming. This required a new programming paradigm, and as we know, this was a significant leap in software design, even more than the object-oriented programming, some people say. So we already know about data communication, synchronization issues, dependencies, scaling. We had to face Amdahl's law and so on. So both architecture and software knew big changes at that time. I just mentioned a few of the challenges that we had to face. So we know about dark silicon. We had many cores then, but we could not use all at the same time because we could not cool them down sufficiently. So thermal issues, power hazards, and so on. Energy became critical. That's why we have experts in energy efficiency to discuss how we addressed such challenges. In terms of software, these new programming paradigms required to translate software in order to exploit the new hardware that was becoming available. So we had legacy software that had to be translated. We also had to create new parallel software, but also we know that parallelism is difficult and still regarded as error-prone. On the other hand, automatic parallelization still remains the holy grail. So we are going to discuss some of these issues with the panel members. And also, we are going to have a peek into the future. So we just heard before that we have no longer just multi-core, but now we have many cores. After many cores, we went through distributed computing, grid computing, which was very popular when the Large Hadron Collider was introduced. From grid computing, we moved to the cloud. And now if we look further into the future, what do we have? Do we believe in computers that simulate brains? Do we believe already in biology synthesis? This kind of nanorobots that we inject, we swallow, and would automatically cure us of everything? Do we believe in quantum computing? Before we reach all this, let's see what else we had in the meantime. So when we faced the multi-core, we had them in desktops, in supercomputers, but nowadays they are available in mobiles and so on. We faced hyper-threading, vectorization. in terms of many cores, we had GPUs, then we had heterogeneity, a lot of other things to solve on the way, accelerators. We had to deal with large-scale systems, coherent, non-coherent systems, data race freedom, communication in these systems. Then we have now Internet of Things, which become increasingly popular, issues such as big data, artificial intelligence, and so on. So what I would like today is that we start with a discussion of what were the hard lessons that we learned from the past, what is the experience that the experts had, what have they learned until now, and then we would like to see what is your vision and their vision. Where do we stand from now, 5-10 years into the future? And even more than that, what is the landscape, where the multicore stands in this landscape? Okay, so let's get to the very first question. And I would like to ask each of the panel members to address this question, if possible. So the hard lessons that were learned. Would you like to start, Per?
Sure. Hard lessons learned until now. So, yeah, multicores were forced upon us, right? I mean, it was the only way to continue, in some sense. The only trend that was good in 2004 was Moore's law, doubling of the number of transistors with each new technology generation, doubling the number of cores. Enormous challenge for the software community, and I reflect on that quite often, what has happened over those 13 years or so. And I don't see much has happened, actually. It's still very challenging to develop parallel software. But what is really challenging there, one can ask, and really design a parallel program that is correct. I think that can be overcome by most professional programmers. What is the hard thing is, of course, to translate a parallel algorithm into scalable performance so that we get twice as much performance if we double the number of cores. And I do not believe that software developers should do that, because it's like running after a moving target. I mean, if you tune your software to one machine with certain characteristics, then you cannot port it to someone else. So what is really the important thing is to put a lot of efforts into parallelism management, and that's something I'm very interested in research-wise myself, resource management, things like that. You mentioned the Holy Grail, order parallelization. Not much has happened there either. It's an enormously hard problem. About, what is it now, 15 years ago, I got very interested in a hardware approach that can help order parallelizers, which is called thread level speculation, where in cases where the compiler does not have static knowledge about to resolve dependencies, and then the hardware could help, or at runtime you could help making decisions by having efficient data race detection, right? And I really strongly believed in that, so I convinced 2 PhD students to work on that. And of course they got their thesis, but I mean, we concluded at the end of the day this is very hard. I mean, we could not get much better than a static approach. And there have been other researchers looking into that, and it's like not much progress. So I don't think, I mean, there have been enormous amount of efforts put into auto parallelization. I think it's very, very hard, very, very difficult problem. Maybe I should not eat up the time here. I don't know.
So I think this just moves us to the next speaker, which is a great connection. So you were mentioning software hardware co-design as a solution to thread level speculation. So indeed, it was not fully solved, but still it was successful on a limited class of applications from what we know, right? But in terms of software hardware co-design, what were the main lessons that you have learned in your experience?
So if we look at the specific example of graphics, then we have a fixed use case with a limited number of people that want to work specifically with that use case, and then we want to design hardware for that use case. We have APIs for that use case since 25 years, and within such a class, people then build up an intuition where programming is inherently parallel. Everything is in terms of pipelines and the threads executing along that pipeline, and then we can tweak our hardware designs for that problem. But still looking at coming from ARM, a system that uses more than 10 watts, that's a large system. And therefore, the problem we have is limitation in power usage. And seeing how we now try to make things more efficient than last year and the year before, we see that it's not only enough to tweak for a programming model for a specific class of use cases. We also look at individual applications and say, now we care about these 200 applications. We don't care about anything else. And how can we rebalance the buffer sizes, the bandwidth between the different units in the GPU and so on for that. So what I see in when we look at GPU architecture and looking forward, it's that the hardware becomes more and more specific. So CPUs are general purpose, and we talk about auto-parallelization for general cases, but a few years ago, we had the parallel programming model working, and now we're working towards having the GPU architecture tweaked for special use cases. And then we could look at in GPUs that are multi-core architectures, we have all the same problems as discussed for CPUs. We have caches and invalidation and protocols and problems like that. But all of that then has to be tweaked for the specific use case, because then we see what patterns of memory allocations are different. And when that pattern changes, we change the hardware along with that.
Thank you. David?
Okay, so I'm mainly hardware and architect design, and I come from the low power multi-core design. And originally, basically, the development of multi-core design was related only to increase the performance of single core, because the technology was not providing enough performance, enough frequency to match the specific target of different applications. As highlighted by Sean, now the main limitation in several application fields, which is in embedded platforms such as mobile phones, but also in servers, is related to power and thermal issues. I think that in this perspective, multi-core can provide a partial solution together with heterogeneity and application-specific or domain-specific accelerator. And what I've seen in my research in the last few years is that if you can operate in a more energy-efficient point, you can improve the performance for a given amount of power by putting several processors, several core in the same die. And you can apply this approach by reducing the supply voltage of your circuit. So if you operate in a super threshold domain, when basically you operate at the nominal voltage of a chip, you operate in a very energy inefficient operating point. While if you can reduce the supply voltage, you can, of course, you reduce the operating frequency of your chip, but you can recover the performance degradation with parallel execution over multiple cores. And this is a way to solve problems related to power and thermal issues in several domains, I guess. The other point is heterogeneity, but we can discuss it later.
Sure. I'm sure that Stefanos will want to catch up on that.
Okay, so what's the question? I agree with all the so yeah, I mean, multicores were forced upon us, right, because of power wall or the energy wall, and that was a convenient way to get to more efficient architectures. And as Per said, and I completely agree with him, programming, parallel programming is very hard, and automating this, maybe it's a El Dorado kind of thing, but if we think about, are multicores successful? I think they're widely successful. We cannot imagine anything else that would be in our systems today, right? So, and why are they so good? Because we run lots of serial programs, right? So Google builds huge data centers with multicores, and they run throughput programming, okay? And they're very good at that, and they have been optimized, and there has been a lot of policing underneath, right? So we tend to think of multicores haven't changed so much, so we started plopping cores on a die, and that's what we do today too, just plop cores on a die. But they have been polished a lot underneath, especially the cache hierarchy, the memory system, memory schedulers. All of these things have been tuned very, very well to run, I think, mostly throughput workloads. I don't know if you agree with me,
I agree.
but this is what most multicore runs, serial programs. Who believes that? What do multicores run today? Serial programs or parallel programs? Serial programs. Lots of threads, parallel programs with lots of threads that have no sharing whatsoever. Serial programs. So that's the case. And why is it so hard to have parallel programs? Because if you start sharing, then things like cache coherence get into play, and consistency models, and becomes difficult, and becomes unscalable, right? And if you think about the other end, right, so we build supercomputers. Okay, how do we program supercomputers? Message passing, essentially, right? So they're big nodes, multicores, and yeah, there's shared memory within one node, but over the whole system, it's message passing. And they just pick the right algorithms that scale well in this context, and they pick the problems that can run in this. So that's why there's a push to exascale, right? Otherwise, it would be totally not worth it going to exascale if we couldn't have programs that scale that to that level. But again, these problems are the problems that are massively, embarrassingly parallel, very little communication, and we just need to do lots of calculations, I think. So there are very hard problems at the core of it in making parallel programming more prevalent, and we are looking at some, and we're making progress. But again, yeah, okay, so we're getting into discussions, the data center as a computer, right? Yes, I agree. That's a hugely parallel computer that mostly works with message passing, right? So you distribute work to nodes, and the nodes are usually multi-socket, multi-cores. But if you look at what runs on each core and whether these threads communicate with them, I would bet that they're mostly like single-threaded code. They might have some sharing, but not that. Most of our software is now multi-threaded, but I don't know the level of sharing that goes on in there. I mean, the Mozilla Foundation there can say, Mozilla starts hundreds of threads. How much is the sharing in there? When I start a browser in my multicore at my laptop, what's the So we run lots of serial programs, and they're good at that. And I don't know why, but it just happened to to find, multicores happen to find a very sweet spot in aggregating resources, right? Who can today even imagine that Google would build a data center with computers, right, motherboard computers, with a single core? Can anyone imagine that? No. Why? Because multicores offer some aggregation of resources and reuse of the memory hierarchy, of the main memory, of disks, networks. I don't know. I don't know how this happened, but it happened. And it's a very sweet spot. And everyone likes it. And it works perfect. And we can optimize it and take it further. But I don't know. On the other hand, something else happened, right? So again, we said, yeah, parallel programs don't scale, but there are some things that scale extremely well, and they're very valuable. Graphics, right? So there we started having GPUs, right? And GPUs are, yeah, multicores, but we came to the realization that you don't need to fetch, decode, execute, write back every instruction. You can do SIMD, you can do, you can reduce this pipeline waste that exists in the general purpose multicore for specific workloads. And for me, this started the whole acceleration thing. And we came to realize that the more we can build parallel accelerators for specific workloads that fit very, very well the workload. Therefore, we can gain significant efficiencies. I won't go any further than that because this will come up. So,
well, we can go on to the next question unless there are more from the audience.
So, so multi-cores are successful for the applications that are throughput oriented. But did we really move to multi-cores for these kind of applications? Were we targeting these applications that caused the move from single core to multi-core?
I think not. I mean, no one would, there's no demand for single core processors, right? If Google had to gain from it, there would be lots of demand for single core processors. But I don't see anything like this. Oh, wrong answer, okay.
So first of all, as I said, I mean, that was the multicore was the only way to go, right? So that's it just took advantage of the only good thing in the future, doubling of number of transistors. But it's very interesting. I mean, if we had an alternative, how would we use the silicon? I mean, so successful that Google and other big data center users are, wouldn't they be that successful? Maybe the computing landscape would be different. It's a very interesting question, but I totally agree with you that, I mean, multicores are actually well used, with the computing landscape as it looks like. That's interesting, at least for data centers. Yeah, I agree with that.
And we should not neglect high performance computing as well.
And high performance computing too. Sure.
There is one more question from the audience.
Yeah. So I agree with you that multi-core processors bring everything on the same die, and that's why they are fast for single-thread programs. I also think that multi-cores are fine for parallelizing a single-thread program. I think that is also an important workload or application for the chip vendors. So do you think that the reason that the predominant programs that multi-core processors run are serial programs is because of failure in parallel programming education? Are programmers simply not competent since the past 12 years to pick up multi-core programming as a first-class technique? I mean, I don't see it still being taught heavily inside universities. Programmers don't seem to know about even Intel TBV and OpenMP. So do you think this failure is an important reason for multi-core not being used for what they're built for?
Should I go for it? Okay. No, as I said, most of our software today is multi-threaded. If you take any program that runs on my laptop, or lots of things that run on the data center, and certainly everything that runs on a supercomputer, they're all multi-threaded software. So, but the threads look like serial threads. There's very little sharing, right? So that goes back to the problem of not being able to scale things that share a lot. That's a serious problem. But I think we have moved well into writing parallel software, as long as it doesn't communicate. I think we are teaching our students early enough and quite a lot of that. It's not, I don't think it's a matter of education. Today, lots of students learn about parallel programming, and they are going to write parallel code, and they are going to do a lot of things. It's just what Per said. It's very hard if you go to certain algorithms, what we imagine, parallel programs in our minds, where you have this shared memory and all the cores bang on this shared memory and shared data, shared every byte and every word and every floating point. This is hard to scale. And we should just simply not expect that we can scale, we can take any program and parallelize it and scale it.
I think that part of the success of throughput computing on a GPU, for example, is given by the very clear and, let's say, easy, or if not easy, accepted by the community programming models. Because all these programming models, such as CUDA or OpenCL, have been accepted and widely used by the community. And this increased a lot the usage of this throughput computing architecture over all the world.
Well, I was just wondering, do you think it is feasible that with the current style of computer architecture that we actually can achieve proper parallel processing, or do we just have to restructure everything from the beginning?
I think we're going to parallelize what is of a lot of value, right? So graphics, neural networks, maybe in the future graph analytics. Things that are of extreme value, we are going to parallelize that and do whatever it takes, which means that we can go to specialized hardware to do that. We don't need multicores to accelerate everything. And in fact, it's as I said, the argument is that you can be much more efficient if you go to specialized hardware than just using, thousands of fetch, decode, execute units to run instructions, the old style. So my view is that we are going to parallelize what is the most bang for the buck, the most valuable things that can be scaled even with special purpose architectures, and for the rest, it's fine. I think everyone's happy with the rest of it.
So maybe that is the reason why we will still have single-threaded applications and multi-threaded applications coexisting. I would like to go on to the next question in the interest of time. So what is your vision about future, both computing and multi-core computing? So what do you see, what will be our reality 5-10 years from now?
Should I start?
Please.
Well, so from a computer architecture perspective, Moore's law that has been very effective ever since the beginning of the 70s is, starting to fade away. Right now, so actually it will stop when I believe that we will be able to scale down the transistors to 5 nanometers, and we are now like less than 2018 or something like that, I think. So 2025 or something like that, then probably Intel and others will give up. And that's interesting, because then for sure, if that is true, then that's will stop multicore scaling for sure, right? So we just have so few generations left. Should we give up with computing? Oh, no, 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 no. In fact, that's when the fun part will start for computer architects, right? And the big challenges will be to use the resources much more efficiently and supporting the software community in an efficient way. And at the same time, what has been haunting us for several years now is to compute very power efficiently. And that will, of course, continue to be true. No, I don't think that, Moore's law will end just like that, because it always happens that there will be innovations and tricks to be played to continue that. But for sure, we go into a very interesting time as far as computing is concerned, and especially for computer architects. So, although I don't have that many years until retirement, I cannot retire when it's so fun. All right.
So you were mentioning that it may be that the multicore will end soon, 2025 already. We see a time limit on it. You believe on that, right?
Yeah.
What does the audience believe about that? What
Well,
do you think will replace it?
yeah, okay, let the audience. Yes, but what I think is needed is, big innovation here. We're going to have to use transistors more efficiently, and that could trigger new computing paradigms, actually. Oh, of course, yes. It's not the end of the world. We're going to continue to compute even more in the future.
What about unconventional computing?
Sorry?
What about unconventional computing?
You had a few unconventional things. Where is this slide? We don't need it, right? You said quantum computers is going to come and save the world, right? I guess what the audience think, if the audience believe that is true. I can say what I believe is true or not true. So quantum computing is not going to save us, not for the next 3-4 decades, or maybe never. What quantum computers are, is an accelerator. For some niche algorithms, it might potentially be great. I don't understand how they work. That's the first thing I have to say. But when I really ask questions about, I understand kind of the computer science part of it, and it's not a general purpose machine. So that's not going to save us, right? You also had neuromorphic, right?
Yes.
Yeah, if we're interested in deep learning and stuff like that, that's great, right? But it's again accelerator paradigms for me. It's not what we have been doing over all these years.
So what will be the future of general purpose then? General purpose computing?
So again, I think, so the compute stack, as we have invested so much effort in, we cannot just throw that out of the window, right? So it boils down to computer architects to really continue what we are going to call it, not Moore's law anymore, but some other guys or girls' law, but that's going to continue. Maybe we should give it a name, but we have to continue to use resources more efficiently, and there is huge room. It's like, if transistors are for free, we of course waste them, right? So really, how computers are not using transistors very well to start with. So I think there's huge room for improvement, and as I said, I like to continue for another few decades as a researcher.
So multicore is not dead. Johan, you were about to add something.
I was about to say that while the cores are changing, the multi will, over the next 5 to 10 years, I think, stay the same. That means that the caches will have different priorities and we will value different things, but many of the problems that have been addressed here will remain conceptually, while the solutions will be different in the details. So we're seeing now lots of startup companies trying to build accelerators for machine learning for the mobile embedded space and talking about IoT and intelligence in every small thing that exists. And over the next few years, we'll see what the use cases are, what the application-specific processes are, but I think that there will be a lot of multi-core if I get to choose a very different kind of core. So I think that when you talk about the 5 to 10 year time span, it will look the same as today, where GPUs are a large part of the multi-core thing from my point of view.
So we expect to see accelerators and different type of cores, but still multi and many cores in the future.
And there was an announcement recently about the new Google branded phones, and they have a new accelerator, probably from one point of view for image processing. And that also has a multi-core architecture. It has caches, it has a number of cores, it has something to control and synchronize things, it has a parallelizing compiler and a runtime stack. And all of this has a different shape, but it's built from the same ways of thinking as has been used for CPUs.
David,
Yeah.
anything more?
So I tend to agree. And so basically, I think that dedicated hardware accelerator, of course, are hundreds of magnitude more energy efficient and powerful than a general purpose processor, but they can be used only not for specific applications, for specific kernels. For example, if we take as an example the CNN, okay, which are very widely used applications. So the part of the CNN that can be efficiently accelerated with an hardware accelerator is the convolutional layer. So the fully connected layers that are part of the CNN, which are basically memory bound, okay, they don't get much with accelerator. So in my view, there will always be this trade-off between multiple cores, multiple general purpose processor plus accelerators. And what I see in the middle, and this is linked with the last presentation, is the use of FPGA. So I really see a big potential in exploitation of FPGA in several domains, from HPC to deeply embedded computing. What is really missing there is a set of software tools that allows to program the FPGA with a very high level abstraction, but still efficiently map the applications which are described with this very high level abstraction very efficiently in the hardware of the FPGA. This is the very big challenge that has to be addressed in the future for what concerns FPGAs.
So more accelerators. Stefanos?
Yeah.
Yes, I totally agree. I think, I think this is the way things are going. We're going to see accelerators everywhere. The question is where exactly the ball will land in this new thing, right, in the roulette. So I believe my personal view is that we're going through a change now, which might affect the whole interface of hardware to software. And whether we're going to have accelerators, fixed function accelerators that do something and you just have a function call and you get a result in software, or you actually can program these accelerators so you have something that's more general than just a specific function and you can program them, the software can program them either, let's say you have a convolutional accelerator that does essentially matrix multiplications, right? And you can just write the software for it, or you can even define gates and multipliers and what have you, like the Accelerator approach, which is totally reconfigurable. I don't know. I think we're going through a transition, and we'll soon see where this is going, and that's exciting and interesting. Before, just a moment, let me just put something here before I forget. There's also the question of memory. Per and I have worked with memory for ages, the whole memory hierarchy. Memory is a huge part of computing. We tend to forget, and we talk about the compute part, you know, doing the additions and the multiplications, but memory is like more than half of computing, and we would like some questions about this afterwards, I think all of us.
Okay, the first question.
Yeah, I was just wondering if you saw the end of centralized computing, I mean, clouds and things. We're going into a trend now where we'll have terabyte memories. I mean, this is already 200 Cray 1s. All the power of the computers is in the edge network. I believe computer data centers are using about 6% of the world's energy, and that is increasing more rapidly than it should. In fact, we've got far more computing power in the edge network, and as soon as we've got petabyte memories as personal computation powered by solar panels and things like that, we've got far more computational power than we ever need. So would you see this trend of sort of centralized computers full of multi-cores splitting into personalized computers controlled by solar panels with all your personal data out in the edge network and just doing it? You know, we've got far more computer power than we need. The problem is we're not utilizing it properly. So it's the kind of resurgent of distributed computing, putting the data back into the edges where it should be.
It's absolutely true that what is very wasteful in computing is moving data around, absolutely. And something that I know that there are a lot of people looking into right now is near memory processing, so that this is something one looked at, was it like almost 20 years ago? There were a lot of projects on that, but it was not so relevant at that point. But now it's really, really relevant, and to get rid of this old model of you know, bringing data to the processor and do what you're supposed to do and then put it back. That's yeah. I mean, yeah. So that's definitely gonna there's gonna be a lot of attention to that, and that could yield also. I mean, this is the time for new paradigms to show up, of course, and I totally agree with you about accelerators, and how it's going to land is, of course, an open question. But near memory processing is something I strongly believe in.
Thank you. There was a second question. You have the microphone?
Before we go on, can I say something about, but you talked more about computing in your mobile and versus computing in the data center. That's a fantastic question. My view again is that this has to do with higher powers, Facebook and Google and Twitter and things like that. So it has to do with the success of the social networking in the population, in the global population. It has to do with things that impose some models of, you know. Yes, I mean, if someone comes up with something that works on the edge only, then we will switch, definitely. That's my answer. I think it's more of the killer app than anything else.
Right, I think it's about the large monolithic applications that would be difficult to split to work on the edge, right? Was there the SETI approach? Are you familiar with that? Looking for extraterrestrial life by using our own computer, so everybody in the world could contribute to that. Similar. So there was a project, SETI, looking for extraterrestrial life, so everybody could contribute with their laptops. Is it something that goes on with this question? Because there was another one in the pipeline. You had something.
It was the same topic, talking about computing at the edge and the roles of Facebook and others. And one argument I've heard is that if everyone's phone can do neural networks and they can do this kind of data processing on the phone and then transmit a smaller amount of processed data to their servers, then they get the same amount of value, but they need fewer server farms. So it's also cost saving for them, because for them it costs nothing if it's everyone's phone doing the work. So there might also be economic pushes towards having that in the phones. And we see now that the expectation is that every bit of compute power relating to neural networks that will become available in the phone will be used. So at the same pace as we increase the available hardware, those companies will increase the use of that hardware, and their applications will become more and more complex and make use of that.
Thank you. I think we have time for one last question.
Yeah. So I think I would like to add to all these things, what I've been talked about, that what lessons we have learned and also how we see it in the next 5 to 10 years. So what I feel, or what I think, is that up till now we have only looked at the things in a very, let's say, specialized manner. For example, researchers in the multicore community, they have tried to find out, okay, how many cores we can increase per year on that one. And then we look at the memory systems, people, they are working on that, how we can improve that one by the order of magnitude, whatever performance that number is. But I think what I see is this lack of integration. So for example, what Maxeller showed is that, okay, now their card is available on the cloud, but the question is how it is connected with the let's say host server. So it's, don't you think that we also need a considerable amount of research in the interfaces between these different let's say devices? I mean, you are talking about compute memories or near memory services, or Samsung talks about in-storage processing. But the question is, do we need a better system balance for our servers? Because probably the big data workloads, they may need a very different system balance compared to the HPC workloads. And the HPC workloads may need a very different system balance compared to the, I don't know, the desktop workloads.
So we have an increasing diversity both in software and in hardware.
Yeah.
How do we interface the two? Is that the question?
Yeah.
Yes, that's the question.